All right, week 106. Welcome to week 106 of building my own operating system. Thanks for joining. I think I will just try to kind of get into it. Yeah, setting up the windows and everything. Got the Intel manual, which may come in handy. So today's focus is sort of two things. Last time I got started on converting the code base to use Intel assembly syntax instead of AT&T syntax. And that's kind of a slightly boring topic, but I kind of got halfway through with that. So I'd like to spend a little bit more time to make a bit more progress on that. And after we work on that little bit, I want to go back to the interrupts thing and see if we can make some more progress on interrupts. Lane 1313, what's up, Lane? I'm going to pop in a test 0 into the chat as usual. All right. So yeah, let's slowly get into that. What's up, the code guy? Sorry to ask, can you say, how is display like this? I'm using a terminal. This is Tmux. And I just have some panes. So it's nothing complicated. It's just it's like a terminal window split into a couple panes. Learning more about LL and LR parsing grammars, compilers course. Very cool. Nice. I don't know too much about that. It's been a very long time since I thought about that. I took a compilers course once in college, but that was always the more theoretical part that I never quite connected with so well. So it's cool that you're learning about that. All right, so brief recap. Last time, this is what we were working on, converting some stuff to Intel syntax. Not really the most exciting feature per se, but just sort of a long time annoyance of mine that we had all this AT&T syntax around. So we converted one file, and that was already pretty good. You can see that Intel syntax is a little bit nicer in some ways. You don't have these percents everywhere. You can just say the register names. Makes it a little bit cleaner. Yeah. Do you grind on LeetCode too? No, I do not grind on LeetCode. I do not grind on LeetCode. For me, that's not really that important. I'm not really trying to pursue a job or anything right now that would require me to grind on LeetCode. So, yeah. Sub Tech Leaf. Thanks for the content. Keep going. Thank you. Thanks for tuning in. We got a pretty active chat already. This is cool. Cool. Well, I hope you're all having a nice Sunday. Okay, and then what I want to show you is, so this is compiling, and I now have a bit more stuff here that's failing to compile, and that's maybe what we look for. So so this is not compiling, and let's just check out what's in this change. So the main idea is, previously the way I was incrementally porting the code base to Intel syntax was I was actually using this directive, but only in a single file. And the nice part about that is it's a very local change. I don't need to modify the build system. I don't need to modify really anything else. I can just put this directive in there, convert this file locally. Yeah, and then we have some inline assembly in other parts of the kernel that I've kind of inherited from, yeah, like the JOS OS, which I kind of forked off of. And I wanted to port some of that too. Yeah, what's up, Tornado? Hey, yeah, what's up, Kobe Wills? How long have I been doing C++? I would say I've been doing it seriously for about 5 years. Had a bit of experience before that, but seriously for about 5 years. Yeah. I think LeetCode, I think there's a place for LeetCode. I think there's certain good aspects of LeetCode, certain skills and algorithms and data structures. But I will also say I've been a professional developer for a long time, and it's relatively rare when I deploy those kinds of skills. And that's perhaps the nature of the jobs I've been working. I think I would tend to agree. I would say maybe go for a balance of maybe like 70% projects, 30% LeetCode, something like that. Unless you are really going for a job that really requires the LeetCode skills, I'm inclined to say, yeah, go for the projects. They're a bit more fun anyway. You get to try things you care about. So yeah. Okay. So here's my attempt at porting the rest of the code base over to Intel syntax, and I was having some problems. We have a warning which we can ignore for now, and now we are running into some issues using unknown. Instruction mnemonic without a size suffix. So I think I just need to understand this a little bit better. So maybe this is a good starting point, this LIDT one. Let's peek into this. Wow. Okay, let's clear some of this stuff out. K-main. LIDT, I think, and then we're calling into this thing, right? And we're talking line 108. So do not mind me if I just pop into the agent a little bit, pop into the AI, because this is some stuff that, or no, okay. So I'm just gonna say, okay, when compiling with Intel syntax, I now get this error. How might I fix it? There needs to be some kind of suffix apparently, because so the assembler can infer the size. Okay. Wow, that is... Yo, what's up, Lizard? Long time no see. Good to see you. All right, excuse me if I just don't check the chat for a little bit. I'm just gonna try to lock in a little bit. This is interesting. Use M. Okay, I'm just gonna, just to say, please make the change. This is a very arcane detail of inline assembly. Please suggest a change. And I'm understanding that it's, oh no, it's finding some wrong stuff. Okay. Okay. Ignore struct sudo desc. That is dead code that's not used. We are using IDT register in trap.hpp now. What's up, Saran? Okay, so it's saying the interesting thing is we never actually saw an error for the LGDT thing, but maybe that's because that function was never called. So what difference are we seeing here? We are seeing we're no longer using the register operand, if that's how it's memory operand. The R and bracket pattern hides the operand size. Fix it by using a memory constraint and no brackets so the assembler can infer the size. That is definitely some inline assembly mastery that I don't have. And also, it's really not the most important thing here. So, just capturing a bit of what I'm seeing. So let's try this out. And so now it's saying don't use the R and the brackets, use the M. And why do we, I'm going to ask it a question. Why do we need a cast to a type? Because I don't really understand why that's necessary. Why do we need to cast the type here? Why isn't a void star enough? So yeah, as you can see, I'm trying to have a balance between vibe coding it and using my brain. So I'm trying to be a bit, because inline assembly, memory operand and the Intel syntax must know the size of the memory operand. A signed, wow. You know, I don't really know if that's legit, but let's give it a try. So that actually did seem to fix things. Okay. Okay. I'm gonna keep asking some questions. But doesn't load IDT load a pointer? You know, that's the really confusing thing. It's in order to engage our interrupt descriptor table, we have the IDT, but then we don't directly load a pointer to the IDT into the IDT, with the LIDT instruction. We have this notion of the IDT register. I think I even took some screenshots in it earlier. Maybe I didn't. Yeah, there's this notion of the ID the LIDT register. Okay. Yeah, I'm just gonna ask a question. So, and I'm just gonna take the time to really make sure I understand this, rather than glazing over it. So, I understand that the LIDT instruction needs to load the IDT register, which is basically a struct with a limit and a base. But what does the LIDT instruction actually take as an input? Is it a pointer to somewhere in memory pointing at this struct? Yes, LIDT takes a memory operand that points to the descriptor in memory, and is that what we're seeing here? We're seeing something like LIDT memory operand specifies a 6-byte okay, so okay, let's, just to make sure I understand, I'm going to try with something different. So I'm going to accept this. Oh, interesting. We need to include, we have a new include now. It's kind of interesting. So I am just going to, but this, okay, this is interesting because we are dereferencing the pointer now. Okay, that's the part I'm not understanding. I'm not understanding the difference between the R memory operand we previously used and this new M operand. It seems like previously we could pass an opaque void star and load and pass it straight to LIDT without dereferencing it. But now it seems with the memory operand, we need to dereference the pointer. Please clarify. And even before I actually, I was hoping to run the kernel to even see if it worked, but we still have these errors. So I'm just wondering, can I quickly fix this? I'm just going to ask the question, one thing at a time. Wow, we got 26 people in the chat. That is significantly more than usual. Wow, that's cool. Thanks for tuning in, everyone, and watching me learn about these details about x86. Okay, let's read the answer. And so, short version, means put the pointer value in a register. Use that register as an address. That's a register operand, not a memory operand. So the assembler can't infer. Means treat the memory at that address as the operand. Yeah, I don't really love, I don't love having to put this type here. It doesn't really seem necessary. But then it was saying having the type here allows the assembler to infer the size. We're not referencing runtime, we're only encode the instruction with a known size. Wait, so my question is, okay, so the compiler can see the size of the type and then know to use the 64-bit version of the instruction as opposed to the 32-bit one? The typed size just lets the assembler accept a size memory operand. Okay. Alternatively, can okay, actually, to be honest, I don't like that change. I think I'm going to reject that change because I don't like that we need to include this header now. Really, it should be totally enough to pass an opaque pointer, an opaque void pointer into this thing, and then LIDT really should not care about the type of that pointer. And so I just do not like how we need to include this header now. So I'm going to, where is that change? I'm going to manually just put this thing back in here. Oh wait, no, it was actually, or sorry, no, it was here. So yeah, I want to make it work somehow with the void star. I would really like to not include that header. So let's get that back. I feel like I'm very confused. Why am I not seeing that error anymore? I'm going to reject all these changes and undo. So maybe going to stage the ones that, just to clear some of this stuff up. So I'm just confused. I feel like I'm not seeing the error anymore. Like at one point, this is why I take screenshots of everything, because I feel like computers just gaslight me all the time. we definitely were having a problem. But it's this bracket. Wait. So it used to have brackets. Let me just check my stash real quick. What was in this stash? That's what, so I'm not quite sure what happened to that stashed entry. But this is interesting that it seems like the brackets or the parentheses are making a difference. Now I'm going to expect to see the error. Let's just verify that. Okay, yeah, we're seeing the error again. And allegedly changing, it's almost exactly the same line, except we're using parentheses now. And we don't see the error. So I want to ask about this. It seems like using parens actually fixes the error also. What's the difference between using brackets and parens here? I'm like, okay, so this is so confusing because it, what? Yeah, what, okay, something is up with the, It seems like we're not using the flag actually. Let me walk through this a bit more slowly. So in this commit, all we do is literally just modify this one file with the directive. And now I'm trying to introduce this to more of the actual kernel. And so I'm starting to pass the masm intel flag around. And so we're working on kmain.cpp, which is where x86.h lives. And in my build, I've changed it so that we're also doing this kernel target only C flags thing, which I have defined. Let's double check that. Where is that defined? Oh, that's not defined anywhere anymore. Wait, what? There's like some hunk missing. But yeah, that's okay. That is a problem. Let me go to the tool. Is it the cross tool chain.cmake? Yeah, it's like, okay, let me fix this in a more direct way. I'm getting kind of bogged down in a lot of this build system stuff. So for the moment, I'm just going to we just hard code it right in there, right? So now, if I run this one more time, now we're finally getting the flag here, and so that, okay. So this is good. So now we're getting an error because it's saying I'm not using the right syntax or whatever. So now let me just go back over here with the brackets. Okay. That was just some BS with the build system and the flag not getting passed. So let me just run the kernel. How are we doing with the kernel? Okay, the kernel is like running good. Like this is where we left off last time. So, excuse me for that interruption, sort of weird side, like quest sort of thing. This is building and working. Okay, I'm just going to, wait, what? Okay, no, this is still there. Okay, so commit, use Intel syntax for rest of kernel. Okay, and I'm just realizing that we have not had the break timer going, so I'm just gonna go ahead with a 20-second stand up and stretch. Feel free to join me. Okay, cool. So, yeah, we technically, okay, there's one more thing I just want to do while we're on this topic. So, and the one thing that's not so nice is the fact that this flag is copied in quite a few places. So that's sort of the thing I was trying to do earlier, and I'm just going to quickly just try to just and that's back to the thing I was doing, and it's a little bit difficult to name what this set of flags actually is. So this, okay, our flags stack is something like this. We have like some base flags and then the kernel flag stacks on top of that. So the base flags though are for pretty much any code, including kernel lib. Kernel C flags is particularly flags that we use when we're cross compiling for the real target kernel. But it applies to everything in the build, including third-party libraries. And then now I'm trying to introduce this other set of flags, which should apply to, it should not apply to third parties. I'm just gonna kernel C flags not third party. And the reason is because third party libs use AT&T syntax, and we don't want to change them. So now I can go over here and just clean that up ever just a little bit. So now we're popping over here. Lastly, kernel lib. The kernel lib is kind of interesting because it should not really have inline assembly, but I'm just going to include this anyway. So now let's just check if we're still building. We're still building. So that's just a small cleanup I'm just going to make directly right now. Okay. Cool. Okay, nice. Let me check in on the chat. Kind of locked in a little bit there. What's up, Useless? What's up, Vpool? Nice to see you guys. What's up, Street Gamer? What's up, Saran? What's up, Yash? Or Yash Kumar? What's up, Nemo Philist? First time here. Yeah, you should just expect a very real and authentic look at what it's like to work on a hobby OS. That's what I'm just here to show people. Including the not so sexy parts of it, like some of the stuff we were just looking at. But we learned a little bit about inline assembly. But yeah, I'm using VS Code with Vim. Lane is right. Lane is exactly right. Okay, now let's move on a little bit. So, I want to find what we were doing in the last streams, and so we've been on this sort of arc of doing interrupts, and the current state of our progress. Again, I'll just clean up everything here. Current state of our progress is that we can set up a very basic interrupt descriptor table, which is the structure used on x86. And I'm trying to do it in more of this like kind of modern C++ kind of way. But yeah. And then we can actually install it, load it into the CPU, which means it's engaged and it's able to respond and handle CPU exceptions and interrupts that happen if we've registered handlers for them. Currently, I only have a single handler. There's only one handler that exists. It's the divide error handler. And I'm able to test that out with a bit of inline assembly that triggers the divide by 0. And we're actually, I think we did this maybe 1 or 2 streams ago, we are actually able to handle the interrupt, trigger a bit of this initial assembly code to receive the interrupt, but then as soon as possible, move into C++ to handle the interrupt in C++, which is what this handle trap function is. And then we've even implemented being able to return from the trap for sort of an end-to-end test of the trap handling experience. And that's what we're seeing here. So this is the code that runs when we dump the trap frame. We trap return back to the caller, which is where we hit this resumed seamlessly exclamation mark, exclamation mark, exclamation mark, panic. And that's what we see here. So everything is working. And what would be nice to do is to move forward a little bit with this. What that would mean is adding some more handlers for different types of exceptions and interrupts. So I'm just going to call that out as something to do. So 0, got that working, and make this a bit thicker. So handle some more exceptions, interrupts, like maybe GP fault, page fault, stuff like this. We can go through the manual and see what we want to handle. Yeah, that's the vibe. Is this your first time dealing with OS making and stuff? So I've been doing this for about 2 years, actually almost to the day. I mean, I started in February of 2024. So really, yeah, we're pretty much at the 2-year mark. And the last 2 years have been my first experience doing a lot of, or really any writing OS code really. But over the last probably 10 years, I've been gradually exposed to OS concepts, but never writing my own OS. Yeah. So let's just take a look through here. What else? What I want to do is I want to actually add a panic, because actually handle trap is a very interesting function because it should never ever return via normal C++ return keyword. It needs to return via the special trap return. So I'm going to change this panic. And this panic is going to be a long-term panic that is going to live in the kernel forever. And it's just going to live at the end of this function to catch panic. Attempting to return from, or maybe fell, or like reached the end of handle trap without really like without like iReading is really the panic message here. So yeah, what's the point of doing all this? What's up, Prashan? I'm just trying to learn about operating systems. I'm really curious about it, and this is the best way to learn. Currently it's just a basic panic. Yeah, if I ever have graphics, I could definitely make a blue screen, and that's where it would probably go. Yeah, Trolley Cat. Great way to learn low-level things and burn time. Yes, burn time. Okay, so little cleanup there. We can just sort of clean any of this kind of stuff. So yeah. Trap cleanups. Again, all of this will likely get squashed or reworked or whatever. I'm still kind of in the prototyping phase for a lot of this stuff. That's how I sort of consider it. We're not really writing production code for right now. Okay, let's take a look at what kind of interrupts we want to handle now. It would also, I don't know, it would also be interesting to think about our testing strategy for interrupts. I really haven't thought about that at all. It's not, what could a testing strategy be? Testing is always the thing that kind of ruins the fun. It's like, okay, how do we write tests for that? Let's ignore that for the moment. Got to ask, are you using any AI for this? Yeah, I'm using a lot of AI. I was literally spending a lot of the early part of the stream asking questions to the AI to understand the inline assembly stuff better. But I'm trying to not, my rule is that I'm not generating like large amounts of code with AI. I'm using it as just like answering questions about details that I don't know the answer to. So. Got chat very active today. What's up, NSG? Better ways making the panic show the exception caused. Look up the exception name based on the int number. Yeah, dump a stack. Yeah, then we get into some of this luxury panicking. We have fancy stack dump. We have exception info. We got all this stuff. Register dump. Yeah. I would like to get there at some point. Okay, let's move it forward a little bit. So I guess what we're going to do is we're going to implement some more handlers, and we just need to be changing the code here to kind of trigger the exception. I guess that's okay for now. Okay, let's take a look at the exceptions. Okay, so and I'm also just I'm going to quickly reference JOS to see again, just one more time, what kinds of exceptions it's handling. Because there's quite a few exceptions. I don't know if we really need to handle all of them, but yeah, like JOS handles a somewhat lighter set. I mean, it's really not that many. It's like 6 exceptions. Let's handle a GP fault. That's probably one of the most important exceptions to handle. So let's overflow. Yeah, there's a lot of interesting exceptions though. Okay, I want to find this kind of thing. Okay. So let's just put this over here for reference. Okay. I mean, we can also take a moment to maybe try to clean this up. I was calling this handle divide error. There's a lot of things that are not nice about my current setup. Also, my func is dead code. It's called trap.s right now, and I copied over some of these macros for declaring things. Okay, whatever. Let's just go for the GP fault. So for handle divide error, I was choosing the no EC macro. Maybe I'll just rename this while I'm at it. It's like a stub. It's like a trap stub no error code. Is that good enough? Okay. Okay, so I'm just gonna quickly clean up, rename. Okay. Actually, then this thing also trap stub. We'll just call this trap stub. I don't know if, again, I don't know if trap is necessarily the idiomatic word here, because trap has a kind of a specific meaning, but whatever. Okay, so we're gonna GP fault. It has an error code, so this will be a good test of something that has an error code. So let's just kind of do that. So general protection fault, and it is number 13. So now we're going to go over here, or maybe, where was it? Handle. No, it was even here. Yeah, that's not lovely to have all these prototypes in the K main. Protection fault. That's just definitely like big code cleanup. Where do the prototypes live? Any way to reduce boilerplate? Yeah, that's all for a bit later. So so now we have our stub and this. So now we can go over to this thing, and it's time for a quick 20 seconds. Be right back. All right, so now we're ready. We're all set up to do this. And so, yeah, again, this is not, it would be really nice to reuse some of these numbers. Like if I can include a header file over here, then use the constants over here, that would be really nice. But I don't have that right now. Yeah, there. Okay, so then this thing is going to be called general protection fault. Yep. And I think that is like kind of it. And so now we just had this stub. We have registered the stub with the IDT, and now the IDT code is going to kick in, and it is going to, I'll just show it to you over here. So for every one, so basically I have these structs are these IDT descriptor infos, which have an index, a function pointer, an is trap, which is set to false by default, meaning they're going to be registered as interrupts, which clear the interrupt flag. And actually, let me just kind of based off of this. So we pass 0 pretty much everywhere here, which means we're using an interrupt gate. It's actually a bit of a question for me. I think, you know, these exceptions, strictly speaking, are not interrupts. They actually are traps. So I think we could even put the is trap to be true here. I'm going to put that as a to-do. Should these be using is trap equals true? They are not interrupts. That's sort of the thing. It's safer. It's sort of just a conservative choice to call them interrupts and disable the interrupt flag. But technically speaking, I think if a trap comes in, you start handling it, and then an interrupt comes in, that might be okay. Yeah. That's the question. It's okay for an interrupt to come in while a trap is being handled? Question mark. I'm just going to quickly ask the AI about this. Any thoughts on this? I don't know. That was a stupid prompt. I just yeah, use. Sorry guys, I'm locking in a little bit right now. I'll check the chat in a little bit. Use trap gate only if you explicitly want interrupts enabled during the exception handler, and you've made the handler reentrant. For early kernel bring up, use interrupt gate. So basically, I think this is kind of an optimization a little bit. You can see it that way. The safest general thing to do is just always use an interrupt gate, which means interrupts are automatically disabled on entry into the handler, which means no other interrupts can kind of concurrently happen. And that's useful or even required for really interrupt handling where you have external devices and stuff. But if you have a synchronous exception, such as a fault or a trap, then I think you don't need to necessarily disable the interrupt flag. So you've made the handler. Okay, so I don't think I've done this, so I'm not ready for this optimization, so I'm going to keep them all as interrupt gates. Yeah, let me check this chat. What's up, A. Swazin? Good to see you. I'm doing pretty well. Another good day of streaming. What's up, A. Man? Where's the GitHub repo? Currently, there is no GitHub repo. It's just my personal private project. I might make it public in the future if I think it's ready for that, but currently I don't really feel like it's really ready for that, so yeah. Yeah, I don't know what people are talking about. I'm using C++. Yeah, I think there's definitely some pros and cons. I think you need to be a bit careful with C++, especially in the kernel, maybe. But yeah, I'm thinking C++ gives me a lot of nice things, and it would be a shame to not have them. And also, if you ever don't want the fanciness, you can always drop back to basically C coding within C++. So what's the name of my OS? I don't have a name right now. I'll give it a name when I think it deserves a name, but right now I don't really think it deserves a name because it still doesn't really do anything. So yeah. Okay, so that clears up this question. We're using the is-trap false. We're using the kernel's code segment selector to make a variable for this. We're using descriptor privilege level 0. We could even use an enum for this maybe, but that's just sort of, it's not that important. Although it would be kind of cool. You could think of like, yeah, like, enum priv level or something like this. 0 unused, I don't know, unused 1, unused 2, user space equals 3. Something like that. I don't know. Maybe a bit overkill. So yeah, sorry I'm going a bit slow. Let me speed it up a little bit. So now we have this, and so what we're able to do is we can then go here. Basically, what's going to happen is if we do something that triggers a GP fault, we are going to basically get execution in the handle trap function. It's going to dump the frame and then return. But actually, currently we have this very sketchy return where we slightly mod the rip value. That was just for testing that the divide by 0 continued seamlessly. We actually don't really want to be doing that. Yeah, let's just do a basic test. What is something that triggers a GP fault? Does anyone know? Does anyone have a good suggestion for how to trigger a GP fault? I just feel like everything triggers a GP fault, except for paging related stuff. That's going to be a page fault. But I feel like any other basic error is going to trigger a GP fault. Maybe I'll just ask the AI. What's a good example of a basic way to trigger a GP? Load a non-present segment selector into a data segment register. Yeah, like you can do so many things to trigger GP faults. Okay, I think I don't want to modify. Okay. Yeah. Please. Yeah. All right, thanks Nemo for list. I'll catch you later. Okay, so let me just see what's. Okay, so the 0th GDT entry is a null selector. If I load that into a segment register, will it GP? I think it will, right? So that might be my choice. Okay, so it's saying you actually are allowed to load the null selector into DS blah blah blah, but for the stack selector and code segment, that's not allowed. So let's do that. So I don't know how to code that in inline assembly, so I'm going to ask it to do that. So please load SS with the null selector to trigger the GP. Okay, nice. So we got some more inline assembly to trigger the GP fault. And here's the expectation actually. So this is kind of interesting because a lot of these faults are kind of fatal. Like unlike I don't know, unlike a page fault where you can handle it and then rerun the instruction, GP fault is like somewhat fatal, and you don't just retry the instruction necessarily. So yeah, so I'm not sure what we're going to really see. I'm just going to put the panic. Basically, we don't want to trap return. We want to hit this panic. We don't want to trap return and return back to the original instruction which triggered the GP, because that's probably going to loop. I remember we were looking into this the other time where certain faults set RIP to point directly back at the instruction that caused the fault. Some move it forward automatically. Like I think it was only software interrupt exceptions intentionally move it forward. I just want to ask the AI about this. So question about RIP. Some exceptions make RIP point at the PC that caused the fault. Some move RIP to point at one instruction after the faulting PC, so execution can continue. Which exceptions do which? I want to say the majority of exceptions leave the PC pointing at the instruction that caused the fault, but software interrupts, like with the int instruction, don't. Let me see. Yeah, for faults, you want to retry. You might retry things. Oh, yeah. Page fault. Other ones. Traps. This is worth taking a note of. Okay. Anyway, so yeah, for us, since we're doing the GP, yeah, we don't want to return. So, all right, let's just. Okay, something, oh wait. Okay, this did not GP fault. it just hit the resumed seamlessly, actually. Okay, I'm just gonna say this did not GP fault. This did not GP fault. Why did that not GP? Okay. Okay, it's saying switch to an out of bounds selector. That should GP fault. Let's try this out. There we go. Okay, cool. So that is GP faulting, and we can see that we have a D in the interrupt number, which should be consistent with this. D, E, F, right? So, so that seems to be working. So, yeah. So that's pretty much it. Pop it into the chat. What's up, Sooks? Troy Cat got the GP fault from creating a file. Oh man. Bummer. Okay, so that wasn't too exciting. It basically, yeah, it's just working. So now the question is just what do we do? I think I need to find a good goal. Like a goal I want to set is I'd like to have the kernel not boot loop when it triggers some kind of faulting condition, such as like a null pointer dereference or something like this. And let me just quickly check JOS again. I think, yeah, JOS installs it handles this in, it's the page fault handler, I'm pretty sure. And that's where we would catch something like this, where it's a page fault from kernel mode. And so maybe some kind of higher level goal for myself is, yeah, good crash exception handling code that, yeah, prints the type of exception that happened, dumps, registers. I mean, we already kind of have that basically with our function that prints the trap frame. More or less. So I'm just going to do a quick little commit here. Whip test GP fault handling. Okay. So I could just go down the road of adding a bunch of other handlers. It's a little bit mechanical, I guess. We just need to make sure, yeah, we're just, I wonder, yeah. There's faults, aborts, and traps. Okay, be right back for the 20-second break. Okay, I just had an idea. So one thing that's sort of clear is that we're not handling a lot of exceptions. And so what happens if we get an exception that we're not handling? I think a GP faults. I would love to just find out where it talks about this. Basically, yeah, GP fault very often results in the kernel crashing. Like blue screen, things just end there. So yeah, so it would probably be nice to have some actual infrastructure here for handling different types of traps. That's a pretty obvious thing we might want to do. So let's think about that. How might I want to structure this? So the simplest and kind of stupidest way to do it is just to have a big switch statement. Which is basically what JOS does. JOS has a bit of somewhat exotic thing. Check that interrupts are disabled. That's a somewhat interesting assert that we could put in there, because we also have this requirement. We pretty much we want to have interrupts disabled on entry. It has a bit of particular handling for entering from user mode. And then this is basically the main important function, trap dispatch. So yeah, it would be nice if I could have a way to trigger these different exceptions without having to comment code in and out. But I don't really have any way to input things into the system right now, so I don't even have like a shell to try to trigger anything. So that's just what we have for now. So let's think about handling the trap. And so I'm just thinking about naming too. Like this thing is called handle trap, which is sort of a generic name. Maybe handle trap entry point is a bit of a better name. Entry point. Yeah. Okay. And then we might have something like handle trap. Also, just a quick little thing we can do. We can take a const reference. It doesn't need to be a pointer. So I might have the AI do this mechanical refactoring. Yeah, I'm just going to try to clean that up while we're here. Convert this to a const ref. Oh, okay. Okay. Please update those other functions to also take const refs. Yeah, this is more what I'm looking for. So we just take the const ref everywhere. Conflicting types. So handle trap. Okay. Okay, so that's still working, but now we have just a little bit nicer. Yeah, okay. Flip, use, clean up, use a const ref. Okay. So now let's talk about this handle trap. And we're going to pass in the trap frame. And I don't know. Yeah, we can think about how fancy we want to be. But the simplest version of this is going to be trap frame dot interrupt number. And then case 0 break, something stupid like that. So obviously it would be nice to have some numbers, some variables to use for this. Yeah. Okay. I feel like I'm getting kind of bogged down in technical debt, so I feel like that's starting to catch up with me and prevent me from going further, because there's all these questions like, okay, where do these variables live? Where do these prototypes live? Stuff like that. So yeah, let's think about that. So far we have trap.h is sort of the home for a lot of things here. So naturally, obviously, but the interesting thing is, we construct the IDT like so, okay, so naturally these constants could kind of come here. Oops. And that's just a better place for them. A bunch of random stuff like this. I feel like a constants file would be good even. This is starting to become like a huge mess. And these prototypes are also interesting. So naturally these can also, at the very least, move out of k-main, right? So far we've done nothing that's too controversial. We're just moving things out of k-main that just don't belong there. I was just kind of looking at this, so this thing defaults the privilege level to 0, which even means, yeah, which like means we don't even need this. So it becomes quite clean. Then there's just the question of these stubs. Yeah. So currently the workflow to enable an interrupt is you add a stub in this file right here. You also need to add a prototype here so that I kind of don't love that these symbols are sort of like leaking out into clients. So I feel like some kind of factory function might be a bit nicer. Like a make IDT function that just does all this stuff. Yeah, again, these are just some kind of random details. Then over here, no, sorry. Yeah, then over here we want some like infrastructure for handling things. There's a lot of ways we could go about doing this. We could obviously have functions, just like simple functions, but I wonder how scalable that is. And obviously you could have a kind of a table of handlers, which is probably a little bit nicer. So I think I'm just going to start off. Let's just go with the easy approach of declaring some functions, right? So The craziest thing, yeah, like the naming, I'm just going back to this naming. there's all these things to name. There's like the stub and this thing. So now that I'm trying to name this, I'm realizing it has a very similar name to this. So I'm thinking it's a good opportunity to go ahead and rename these. So instead of handle divide error, it's more like divide error stub. Something like that. And even exception, exe divide error stub. Or wait, no, what am I doing? I need the similarly general protection fault stub. Yeah, exe because of exception, which I feel like is a bit of a more general name than trap. Okay, so now that these things are named in that way, that makes it a little bit easier for this thing to be named handle divide error. Right. And then so super basic, super basic. Something like this. So if we just go back and load in our divide by 0, yeah, that's what we see. So that's handling the divide. Realistically, yeah, the handle divide error would maybe do something else. It would kill a process and switch threads. Something like that. But for now, we just have this stuff. General protection fault. GP. It's a bit of a, yeah, general protection is a bit of a cumbersome thing to be typing all the time. Okay, yeah, obviously now. So we need to remember to hook this up like so. There we go. So that's starting to look okay. Dump trap frame. What I want to do, yeah. So trap return now becomes something kind of specific we want to use in certain situations where we really do want to return back. So far we don't really have a use for that for either of these things, because in either of these cases the calling code basically just gets terminated if you hit the divide error. But one thing we can try is adding the software interrupt support. And so let's add a handler for I'm not seeing it. Protected mode. It's probably on the other page, which I didn't screenshot. 6.1. So no. Okay, I'm just gonna grab this anyway. Oh wait, that's how it works. External interrupt or int n instruction. User defined non-reserved interrupts. So that's what we could try doing. So yeah, we could try doing a software interrupt 1. And let me just check JOS again to see how trap entry.s. And so we registered at least a couple. Syscall. Right. So yeah, this is JOS's. So 48. So you have 21 of these, and then up to, so basically there's 32 slots that are either like CPU specific meaning or reserved, and then you can go into the user defined area. So let's test that boundary. Let's handle an interrupt on the 30 second interrupt slot or whatever, gate. So to do that, I'm just going to, do they have an error? No, right? They don't, there's no error code associated with this. And so it's just going to be, let's just make it I don't know. We'll call it syscall for now. Syscall stub. And we'll call it number 32. And we come over here. 32. Oops. All right. 20 seconds. Be right back. So what's up, Mac Henry? Yeah, I run this code in an emulator. I run it in QEMU. Exec, call it syscall, just to be cool. Syscall stub. Yeah, I wonder if it would be so nice to reuse these numbers right here, but I think there will be some problems with that because like I think the assembler will understand define includes, but not this inline context per auto C++ BS. So how to share these constants with trap.s. But whatever. Okay, that's all we need. So now we can come over here and we can fill out more boilerplate. Syscall stub, but we're not trying to call it. And then now we can go over here And yeah, we got to do something about this boilerplate at some point. But now we're just handling this, and then now we come over here, syscall. Okay. So now that's the boilerplate for handling a syscall. Now we're going to trigger a weird syscall from the kernel. Again, there's no user mode at all, and so all this is really going to be is just sort of the kernel interrupting itself to trigger some other handler, and then but then the key point is that it's going to actually return back to the main kernel, the main k-main thread that's running. So now I want to just say trigger int hex 32. And again, I never really learned the inline assembly to do this, so apparently that's it. And so now what we should really see here, actually. So what I'm going to do, I'm going to... so just to start off, I'm going to just run it, and we're going to see the panic on the syscall with the dump trap. That's my expectation. No, we're seeing G. Oh wait, no, but it's not hex 32. It's decimal 32. Change this to dec 32, not hex. My mistake. That's why GP faulted. So we've got the $sign for the 32, and then bam. So we got the syscall being panicked on. We're handling it and then panicking. But unlike these other two exceptions for this syscall, quote unquote syscall / software interrupt, we don't need to panic. We can actually return back to the caller. And so what I'll just hackily do right now, oops, I kind of lost my place, is I'll just put a trap return trap frame straight up right here. Which is going to dump the trap frame. It's going to trap return back into the caller. We're going to hit the resumed seamlessly print. Let's just test that out. That did not work. We are now hitting a GP fault, which I did not expect to see. So that's interesting, but at least we're not boot looping anymore, because now we have a GP fault handler installed. So that is interesting. Why is it doing that? Let's check out the trap return. Was there something weird? I don't think so. All right, I want to just make, I want to go back to our nice little simple divide by 0 and just retest some of this stuff. So what I'm going to do, I'm going to re-enable our hack here. Which is a bit hard to do now because it's a const reference. I'm going to make this... I'm just going to make it non-const. And then I'm going to come over here. Oh, that's so annoying. Okay. You know what? I'm going to use a const cast to force this right of this member. Okay, so we const cast this thing to immutable reference. Then we set this thing. Okay, and then over here, I'm just going to do a similar thing, trap return. So I'm just gonna call this over here now. So we're gonna handle the divide error, dump the trap frame, trap return, and hopefully that should work. We should see the resumed seamlessly. Otherwise, I broke something in the middle of doing all this refactoring, which it sort of seems like I did. Because this thing was definitely working before. That is unfortunate. What is going on? So what about here? What if I just directly trap return in the entry point? I wonder if that that was not working. Okay. Wait. Dump trap frame. Okay. Maybe I tried to do too many things at once. Yeah, so now... Oh, but wait, okay, this is probably because... Okay, shit, I can't even get out of this thing anymore. How do I stop? This is crazy. I need to X out of the window. It's probably because my hard-coded address here is no longer correct. Let me just launch the debugger. Did that not work? Okay, I need to go into the target. Jeez. K-main. BK-main. Continue. Disass. Okay. We can break a little bit even closer. We can break on the load IDT fin. So now we just call load IDT, and this is the address after the div. So this is the address that we need to have hard coded in our weird hack. I think that was the problem. So now let's just try this once more. Kimu. Yeah, there we go. Resumed seamlessly. So the problem was that this is an extremely fragile way to return back to the caller. The whole point of this was just to test whether the trap returning even worked. And we were doing this with a divide by 0, which doesn't automatically update RIP to point to the next instruction. So we need to like kind of manually point RIP at the right place. But now that we have that, now I can sort of go back and go here. So now we can again try to do this. So now it should in handler func. This should work. There we go. So the divide by 0 happens. We are handling it. We handle it in the handler func function, and we trap return it back to the caller and resume seamlessly. So now that is working, now I'm just super curious about the syscall, because that was failing to trap return. And I don't know if we'll have time to fully debug this, but I'm expecting us to hit the resume seamlessly. We should hit here. We should see this print. We should resume seamlessly. But we're not. We're getting the GP fault for some reason. Which is so this is something specific to handling the software interrupt, because we've proven that we can iret and trap return from the divide by 0 exception. That totally works. We just saw that right here. that's totally working. And so there's something wrong with triggering this software interrupt. Maybe I don't really know what the problem is, but let's just debug it. So I'm just going to finish, and then we're here. We are pointed directly at the int hex 20. So I'm just going to do a step instruction, and we should begin to enter the stub, and we totally do. So we're in the stub now. Kind of eyes over here, or step instruction. Eyes over here. So we're running through our entry stub. We're pushing all the registers, and we're about to call into C++, and we're here, and we okay, I'm going to stop stepping by instruction now and start stepping at the function level. So we're at the handle trap. We're now entering the switch. We're here, and so this is all working. So now we're going to step into here. What's up, Kedar Codes? Nice to see you. Trap return. And here we are. My prediction is that the iret queue is the one GP faulting. Let's just make sure that's true. Yeah. All right, we're at the iret queue. I'm going to step one more instruction, and we GP fault. So something is wrong. Something's wrong with how we are returning. I wonder what that could be. Okay, let me just brainstorm a little bit. So capture this. It is so nice to have the GP fault handler finally, though. And at least things don't boot loop like crazy when we iret back from the syscall into 32 handler. What are the theories? Is the stack frame layout different? You know, we could, yeah. Let's do that one more time. I do need to get going kind of soon, but okay, let's break on. Let's just break directly on trap return. There's no reason to step so far here. So now we're in trap return. And what I want to do is I wonder if the C++ change to a const reference could have screwed things up. I sort of don't think so. No. It was, yeah, I happened to do that refactoring in the middle of doing all this work. I somewhat doubt that it's the problem, but I want to break on this add. So I'm going to break on, oops. So I'm going to continue. So now I want to check out the stack. I'm going to kind of dump the stack a bit. I want to dump some, some words from the stack. So we can see, so I'm particularly interested in these things. So the way the trap frame works, sorry, where's my trap frame? So we have the GPR data, the interrupt number, and the CPU data. And the goal of the trap return is to basically reset things to a very similar state at which we entered the trap, because those are the conditions you need to then trigger the trap return. And specifically, yeah, it needs to be pointing at RIP, I want to say. So that's the idea behind our trap return code. It pops all the GPRs off. It pops in the interrupt number and the return code, and then resets the stack pointer to point at RIP. And is that what we're seeing? I don't know if that's what we're seeing. Something seems a bit wrong. Something seems a bit wrong. So we are now at the point where we're about to add hex 10 to RSP to point it here. We have the hex 20, which is the interrupted number, and the error code. Oh. The error code has this crazy value in it, which makes me think that something is wrong. It's a little bit hard to tell. What is relatively easy to tell, can I not disassemble K-main? Oh man. What? Okay, no, I can, X 64I K-main or something like that. Okay, I just wanted to, that's annoying. Okay, I just wanted to lvm obj. Oh man, this thing, it's I'm on version 21, I want to say. Obj dump Intel build target kernel elf. Oh, I need the dash. Oh my gosh, what? Okay. There we go. K-main. Trying to find the div. Okay, no. Here we go. Okay. So So 16.2f is the address after the hex 20. That's where we want to return to. Okay. And yeah, no, that's not. We're seeing that right here. So something happened with the stack. We're about to add 16, but our stack something is wrong with the stack, and it's going to pop it a little bit too far, I think. But then what's this thing? Wait a second, but something is kind of confusing because we have a hex 20 and then the rip. Why are those two so close together? $20 is the interrupt number, right? I'm gonna kill the palm tree. Wait. Something, yeah, I mean, even from this dump here, we can see that something is wrong. Is it as simple? Okay, without deeply understanding this, is it possible that I chose the wrong? Oh, no error. Maybe. Yeah, that's probably the reason. It's probably a stupid mistake. Yeah, it's a no error. There we go. I don't know what this is. Interesting. In syscall func resumed seamlessly. So there we go. I made a silly mistake of not specifying the no error macro because the syscall or the int software interrupt does not have an error. So yeah, so that's my stack got all messed up because of that. But check it out. Yeah, now we are resuming seamlessly from this quote unquote fake syscall. Is anyone still in the chat? We got 16 people in the chat. Yeah, sorry if that was kind of chaotic, but we got that working, so that's pretty cool. So we just basically, just to recap, yeah, fleshing out the I missed all the Twitch chatters today. I was too busy focused on other things. Sorry to all the Twitch people. Yeah, so quick recap. So basically, yeah, just moving forward with the process on handling interrupts. We have a couple new stubs added. Particularly important, we added the general protection GP fault basic handler. A lot of these just kind of panic now, but we have some basic dispatching infrastructure, just function at dispatches. It would probably be nice to make a syscall table in the future and not have this kind of stupid switch statement, so we could add a syscall table later and have all these function pointers in a nice table. That could be nice. Yeah, and so far we showed that we were able to return from a fault. What's the explanation here? Traps bp int db. Aborts are undefined because you don't return from an abort. So yeah. All right. Well, that's gonna wrap it up for today's stream. That's gonna be it for today. I gotta get going. So I'm just going to say thank you for watching the stream. Thank you for tuning in. I really appreciate it. If you're enjoying this content, I would really appreciate if you subscribed to my YouTube channel, if you're watching on YouTube, or my Twitch. If you're not watching on Twitch, that would be really amazing. If you want to keep hanging out, I have a Discord server. Feel free to join the Discord server. The link should be posted there any moment now. Yeah, that's going to be it. And I hope you have a great week, and I'll see you in the next stream next week. All right, have a nice one. Peace.